let's get started for our last session, and we have a couple of interesting applications. But let me just give a preliminary thought here on the Philadelphia crime curves and related to the estimates. Part of the difficulty, I do think that the results are shown in the right order, but I'd like to take a look at that further when we come back. But part of the difficulty here is to disentangle the linear S and the quadratic Q development, which are related to the time scores and are to some extent confounded, but noting that the intercept factor mean is the one that pretty much drives the development here. If you look at the intercept factor mean for class 1 here, it is minus 2.776. For class 2, it's minus 4.342. For class 3, minus 5.607. So it is the low value corresponds to low loads, low probabilities. And I think in this case, it's really the mean that dominates the development, whereas the linear and quadratic are multiplied by time scores that are fairly small. So, you know, the lowest logit value would give a low mean. The intermediate will give a higher mean. Minus 4 is higher than minus 5. And minus 2 is higher still. So I think it's very hard. I actually think it's very hard to interpret the means per se without having access to the plot that combines all these values with the time scores. So my guess is that we have it right here, but we will look into this in much more detail when we get back in peace. So with that, let's get into general growth mixture modeling. And by putting one more G here before GMM, we're really only adding one thing: consequences. Class membership predicts later outcomes. And we already talked about that a little bit in general, where we said that often it is the trajectory shapes that are predictive of later outcomes, not so much the growth factor values alone. So we said, for instance, if you have a low slope, almost zero slope, that could mean that you have no alcohol development problems if the intercept is also low. So the low slope happens here, whereas if the low slope is for a trajectory that's up here, it could mean an early onset development, saying that a growth factor by itself is not an easy way to describe a growth curve shape, but the latent class variable is. So now we have a series of examples here that show the possibility of incorporating a distal outcome that's predicted by latent class membership. And Linda's going to go through, I think, 2 examples that are very similar, but with different application areas. And then I'm going to come back and do an example that has to do with randomized trials and growth mixture models. And then Linda's going to finish off with a sequential growth model that is of the mixture kind. So hold on to your hats. There'll be a grand finale here.
Well, I don't know about that, but anyway, so we're going to look now at 2 growth mixture models, general growth mixture models. One using the LSA data that we've looked at earlier, and with a distal outcome of high school dropout. So that's how it gets its extra G, because we have distal outcome of high school dropout. And then we're going to also look at the NLSY data, again, the development of heavy drinking from ages 18 to 30, related to both antecedents and consequences. So we're going to start at the end on the left screen. So here we have our LSA math achievement. We looked at that earlier. And we have three trajectory classes as shown up here, We have the poor development class, a moderate development class. Poor development is 20%, moderate 28%, and then a good development class, which is the majority of people. So if we look here on the y-axis, we have math achievement. The x-axis is time. It's grades 7, 8, 9, and 10. And you'll see for the poor development, they tend to start lower, and they have a lower growth rate. Moderate development class starts a little higher and seems to grow a little faster, and there's less variability for the poor development class than the moderate. And then our high development class, which has a lot of variability and starts fairly high and grows at a fairly good pace. Now, the extra G in GGMM is our distal outcome. And if we show at the bottom of the screen, you'll see dropout. And we're looking at the end here at the results, and we're going to see how we get these results subsequently. But for the poor development class, they have a 69% high school dropout rate. For the moderate development, an 8% dropout rate, and for good development, only 1% dropout. So you can see this is what we're talking about when we say you can use an auxiliary variable to look at predictive validity. So it makes sense, of course, that high school dropout is going to be higher for a class that has poor development, less high for moderate development, and almost non-existent for the students who have good development. So this is the GGMM model with high school dropout as a distal outcome. Now here's a path diagram of the model that we estimated. So you can see here we have, first of all, our math outcomes with residuals. We have high school dropout as a distal outcome. We have a set of observed exogenous covariates. And let's go through the model and discuss the specifications and what they mean. So we're familiar now with the linear growth model, which has an intercept and slope growth factor. And we have our categorical latent variable C, and it's pointing to I and S, and it's also pointing to high school dropout. So when it points to I and S, it says that the intercepts are going to, of the intercept and slope growth factors are going to vary across classes, and when it points to high school dropout, it says that the thresholds are going to vary across classes. When we regress high school dropout on this set of covariates, so the arrow pointing from the covariates to high school dropout, that's a logistic regression of high school dropout on these covariates. So we've talked about this, and that. Now here we have I and S both regressed on the background variables also. And we have C with dotted arrows pointing to the regression of high school dropout on the covariates, which means that the regression coefficients in that regression are going to vary. We have also pointing to the regression of I and S, saying that though I and S regressed on the covariates is going to vary across classes. So that's what we say in this picture. Oh, and then one other thing to say. So, and Bengt mentioned this earlier, but it's always good to say things more than once. So if you note, we're predicting high school dropout from the trajectory shapes, from the categorical latent variable. We don't have arrows from the intercept and slope growth factors pointing to that. So as Bengt had mentioned, these can be confounded and it can be more difficult to interpret. And really, I think our question is, do these trajectory classes have different high school dropouts? So it's the shape of the curve that we want to use to predict high school dropout. So this is just a brief example. I lied to you when I said we were going to show you where we found everything, but anyway, of LSA math achievement with a distal outcome. But now we're going to go on and look at another brief example, and that's the NLSY heavy drinking. So you could hypothesize that with heavy drinking that you would have two classes. Here, this is the frequency of heavy drinking on the y-axis and age on the x-axis, or the time in our growth model. So one could hypothesize that they have people who start drinking around 18, not too high, get a little higher as they're into their early 20s or so, and then that they decrease in their heavy drinking by the time they're around 30. And we could hypothesize that there are other people who start drinking at a fairly heavy level early and just continue that trajectory. So we could hypothesize that when we do our trajectory analysis, when we do our growth mixture model, that we're looking at for at least two different types of people, but maybe we might find meaningful classes beyond those two. And when we did the analysis for the heavy drinking, what we found was actually 4 classes. And this is with the NLSY data. We found what we had expected, the low class here, people starting out low, going up a little, and then going down slightly. We also found the high class, which starts out high and stays relatively high. But we also found a class that starts out low, but becomes very high over time. And a class that starts out very high, but then reduces their drinking to a level similar to the ones who start out fairly high and continue. So we found the one class we hypothesized, the one that starts low, goes up, and goes down slightly. But for the problem drinking classes, we found more than one that had substantive meaning. The ones who started out low and became high, and started out high and went down, but not to a low level. So if we take a look at a diagram of the model and see what we have here. So we have our growth model that we're familiar with, heavy drinking over time, and we have growth factors. These are continuous. This part of the model, where we have trajectory classes regressed on gender, ethnicity, and family history, and then also some other adolescent measures. And we find results from this part of the analysis in the multinomial logistic regression of trajectory class on a set of covariates. The distal outcome information, so trajectory classes causing alcohol dependence, we find in the variation of the means across the trajectory classes. So if we move forward on this, here's the formula of multinomial logistic regression. So this is the multinomial logistic regression, and we went over those formulas yesterday. That's that part of the model. And that part of the model is shown in this table in summary from the output. So we have the 3 classes, the class that goes down, high, and up. And this is a multinomial logistic regression. So the 4th class is the reference class, so we don't show that here. That's why we have the 3 classes. In the rows, the column here has the names of the variables: male, black, Hispanic, early start of drinking, and then we have 3 family history variables, high school dropout, and expectations of going to college. And so well, let me put the classes back over here. Okay, so we have the up class. This is the up class. So if we take a look at the up class, we can see which covariates are significant. We have the t-value there. So being male is related to being in that class. High school or family history is also related. High school dropout, and a negative relationship to having expectations of going to college. So this is a summary of the multinomial logistic regression. The high class over there that starts out and stays high is predicted by being male, not being black, having an early start of drinking, family history, positive family history, and low expectations of going to college once again. The downward class also has not being male, not being black, not being Hispanic. It's also early start, but not the other variables related to high school dropout. So these are the people who start high but go down. So high school dropout and low expectations of college are not significant covariates for those, although they are for the other 2. So this is when we do the multinomial regression of the categorical latent variable on the covariates. This is to better understand who is in these classes, what type of individuals they are, and what covariates are significant. And then for the high school dropout, take a look at this slide. So we have the classes, the down, the high, the up, and then the normative class, which is the reference class. And we look at the thresholds across the classes. And the part of the model, well, maybe I should put that up again. So this part of the model, it looks like a regression of alcohol dependence on trajectory class, but it isn't shown. We don't specify it in the model command using the on, because what it actually is just simply the variability of the thresholds across the classes. So the thresholds can then be turned into probabilities, as we saw, and here we give the formula. So just to remind you, we have a threshold here. The probability is 1 divided by 1 plus e to the minus logit, where logit is equal to a minus threshold. So the logit would be minus this, and then minus logit would end up being the positive number again. So it would be 1 divided by 1 plus e to the 1.631 would be how we get the probability here. The odds are simply the probability divided by 1 minus the probability, and the odds ratio is equal to the odds for class K divided by the odds for the reference class. So here we get odds ratios, and you can see that for the class that goes up, starts out low and goes up, the odds are 30 times greater for them having problems than for the other classes. There are 30 times greater odds for that class to have high school or to have alcohol dependence, which is the dependent variable then, alcohol dependence. So you can see that that's how we use this. And once again, it's the interpretability, it's the predictive validity. So if you have somebody in a class that starts out low and goes up higher than anybody else, I mean, that's pretty much looks like the worst alcohol behavior that we saw in the other classes, and you would expect that the odds ratio would be 30 times greater for those people to be alcohol dependent than for the reference class. So we're always comparing to the reference class, whereas those who went down have the smallest odds ratio. And those that were more or less started high and kind of just stayed up there, their odds ratio is in between the two. So that would, to me, indicate predictive validity of the classes. So if you, for example, found classes that you believed represented alcohol problems or trajectories of drinking, of heavy drinking, and you related them, and the class that you considered to have the worst heavy drinking, if it related less to alcohol dependence than others, then you would wonder about whether you really have the classes right or if the data are correct, if the data are reliable and valid. So this is this part of the model. So it doesn't end up, you don't end up getting regression coefficients. And if, for example, the distal outcome is continuous rather than binary, as in this case, then you'll have means that vary over classes. And you'll have a different mean in each class, and you can test whether those means are equal or they're not equal. So when you see it, there is an example in the user's guide with a distal outcome, and the only change in the input between the model with and without the distal outcome is that you just add the distal outcome onto the used variables list. So you don't have to have an on statement. Okay. So now for this example, I think we have the output for that. Input. So here we have our categorical variable DEP94, so alcohol dependence. And we don't show all of the full input, so we don't have the names of the variables or anything. But we have 4 classes. The distal outcome is DEP94. And see in the model command, we have the multinomial logistic regression as the first line, C number 1 dash C number 3 on the set of variables. We have our growth model, I, S1, S2, and that's specified with centering at heavy drinking in 1989. That was done, the centering there is explained up at the top. It was done such that the centering age is at 25. The following statements you really don't need. They can be done by the default like we talked about yesterday. But now here are where we get the results. So, for example, here, this is class number 1 on the covariates, 1.214, 1.21, negative 0.89, negative 0.89. So we take the values in that table from the multinomial logistic regression results in the output. So in the output, we have C number 1 on the covariates, and then we have C number 2 on the covariates on the left screen, which will match 1.25 is 1.248 rounded, 1.45 here. So this is all of the information from this table was just taken from the multinomial logistic regression part of the output. Now here, we have the information for the distal outcome of alcohol dependence. So we have class 1, class 2, class 3, class 4, and we have our thresholds, 1.631, et cetera. And if we go forward over here, we'll see that those are the numbers we put in our table. So these two screens can be compared. We have the threshold 1.631, 1.041, et cetera. And then we just compute the probability, the odds, and the odds ratio to complete the table. And the formulas are all given there. And this we've gone over a couple of times. And that's the end of that example. Now we're going to look at a totally different example, unlike anything that we've looked at so far. And it's interesting, it's a sequential process model. So we've looked at a couple of parallel process models where we have two processes, but they take place during the same time period. But with a sequential process model, we have one process and then another process following later in time. And the aim of this analysis is also somewhat different than what we've looked at, and an interesting application, I think, of growth mixture modeling. And what we want to do is we want to use the earlier process to predict a later process. And the major goal here is the study looks at kindergarten. It looks like at children who are at the end of second grade who have had various test scores measured on them from the beginning of kindergarten to the end of the second grade. And what the aim is to find the failing class early. So we know there's a failing class, and we want to know how early between the beginning of kindergarten and the end of second grade, how early we can detect who these kids are and therefore make an intervention before they become so badly behind that they can never catch up. So the paper, Moutain, Koo, Francis, and Boscardin, 1999, and we have a sample of 410 individuals. So there's a lot of information here. So it's longitudinal multiple cohort. So actually it's more students, it says here, but I guess maybe we only look at part of them. So anyway, in grade 1, they take reading and spelling skills in grades 1 and 2. And then in kindergarten, they have phonemic awareness and then a rapid naming variable that we use. They also take a standardized reading comprehension test at the end of grades 1 and 2, which we don't look at. They have 3 research hypotheses, and here's the reference that you can look at for further information. First of all, they hypothesize that kindergarten children are going to differ in their growth and development in precursor skills, so in the phonemic awareness and rapid naming. So they think the children are going to develop differently in phonemic awareness. And they think how the students develop in phonemic awareness is going to be related to how they develop in their other skills in reading and spelling in first and second grades. They also hypothesize that this is going to impact the standardized tests of reading and spelling, but we're not going to be looking at that. And then they hypothesize that the use of growth rates for skills and precursors will allow for earlier identification of children at risk for poor academic outcomes. So they're predicting that being able to see these growth trajectories, we're going to be able to more early identify the children who are having problems. So this was actually a dissertation that was done by one of Bank's students, part of this. So here on the right screen, this is in grades 1 and 2. This is word recognition over grades 1, which is the 5th measurement occasion. So we have 12 measurement occasions altogether. The children are measured 4 times in kindergarten, 4 times in 1st grade, and 4 times in 2nd grade. So this is word recognition in 1st and 2nd grade. And you can see that there are some children down at the bottom here, quite a lot, because the dark lines represent more students, and that are having not very good growth. So at the beginning of 1st grade, they were pretty low, and they're not developing anywhere near as much as students who came in higher or in the middle. So the goal is to identify these students, the students who are having problems, as soon as possible, as soon as possible. So on the left screen is the model, or 2 models, and we'll talk about both of them, but it's the model on the left that was used. So the first 4 variables here are phonemic awareness in kindergarten. The second 4 variables are grade 1 word recognition, and the last 4 are grade 2 word recognition. And you'll note in the path diagram that we have 2 growth models. We have one growth model for kindergarten, and we have another growth model for grades 1 and 2. We have one categorical latent variable, and it's pointing to the intercept and slope growth factors of both of the growth processes, saying that the intercepts of those are going to vary across classes. We also have residual covariances among all of the growth factors. I1, S1 are the growth factors for phonemic awareness, and I2 and S2 are the growth factors for word recognition in the 1st and 2nd grades. We also are using the rapid naming variable as a covariate that explains the class membership. So this is the model that Christy Kim used in her dissertation, Christy Boscardine now. But here's another way that you might think about looking at this, because in this model, you're in the same class in kindergarten as you are in the 1st grade. In this model, the difference between the 2 models is now we have 2 categorical latent variables. We have one categorical latent variable for kindergarten and another categorical latent variable for grades 1 and 2. And so we have included now a latent transition model in this sequential growth process model. And what that allows is that students who are doing poorly in kindergarten have a way of transitioning out of that class, whereas on the model to the left, students are in the same class for kindergarten, 1st and 2nd grade. But here we've added a latent transition model. So people could conceivably move from the very lowest class to a higher class. Now, Christy, after her dissertation, explored this model, and she found that children didn't transition. So, they weren't staying in that lower class because we were forcing them to be there. They were actually staying in that lower class because they weren't changing enough to transition into a different class. Now, here we are using the BIC to determine the number of classes for the model on the left. And you can see that the BIC goes down and hits a minimum at 5 classes. And those are the classes and that's what we decided on, or what Christy decided on. Now, in this analysis, we're not really interested in all 5 of the classes, and that may very well be the case in your own research. We're really only interested in that non-performing class. So we're going to be focusing on them. But before we do that, let's take a look at the input for how you would set this model up. So we'll just focus on the model command because I don't think there's anything else that's really new. So now we have 2 growth curves to specify. So we have I1, S1, that's the kindergarten growth curve. And what we're doing here is we're centering. You notice that the last time score at the last time point is 0. So our time scores here are -3, -2, -1, 0, because we want the intercept growth factor to represent final status, because these are sequential growth processes, and final status will then be related to the second process from 1st and 2nd grade. And then also I2, S2, and we have the same type of issue that we're doing it at final stat. We're making the final status the representative of the intercept growth factor. So we have 1 growth model for kindergarten and a 2nd growth model for 1st and 2nd grades. We have 1 categorical latent variable, and we're asking for 5 classes. We have the multinomial logistic regression, C number 1-C number 4 on rapid naming 4. That's the bottom part of the model over there. So this is how we specify this model. Now, what came out of this were the following, or the trajectories that we see here. So here's kindergarten growth. We have 5 classes. This is for phonemic awareness, and 5 classes for grades 1 and 2 of word recognition. So down here you see we have this very low class. The solid line is representative of the solid line over here. So they mean the same. So these are the students that we're interested in. They start low at the end of kindergarten. Nothing's really happened. They go into 1st grade, and they just sit there. Nothing's happening to them. We have other students who came in fairly low in kindergarten, but they seem to increase, some more than the other. And when they get to 1st grade, they continue to do better. And then we have 2 classes that started out, did well in kindergarten, and then are high in 1st grade with not so much growth. Maybe they aren't being challenged enough. We don't know. But anyway, we don't really care so much about these classes that are doing well. What we do care about is we want to identify who these students are as quickly as we can between the beginning of kindergarten and the end of 2nd grade, so that we can intervene and help them and get them out of this no performance and no growth situation. So the way that we do this is I think I'm going to put this over here so I can go back and forth. But we're focusing on class 1. So the input for the model that I showed you, we estimate that. So the first step is to estimate the full growth mixture model for kindergarten, grades 1 and 2. So we estimate the full model. And the second step is to get most likely class membership from that model. And that's what over on this table, along the top is most likely class membership. So we have 46 people in class 1, 71 in class 2, 144 in class 3, 100 in class 4, and 49 in class 5. So that's the first step, is to get most likely class membership. Then the next step is to take the parameter estimates from that full model, but fix the estimates from the full model of step 1 using only kindergarten information. So basically in Mplus what you would do is you would say use variables equals, and then you would just put the kindergarten variables, the 4 kindergarten variables. Then in the model command, you would only specify the part of the model that applies to the kindergarten variables, but you would fix the values of all those parameters at the values that you got from the full model in number 1. So, and then when you run this model, you don't estimate anything, except you get most likely class membership from it. So you will get a most likely class membership based on only the kindergarten variables. So what class are they most likely to be in at the end of kindergarten? And then you repeat this process for kindergarten plus the first testing time at grade 1. And so you would add 1 variable to the used variables list, the first measurement in grade 1, and then you would include parameters related to that variable in the model command with everything fixed. And you would get most likely class membership for that. And you keep doing that, adding 1 variable at a time till you get the end of 2nd grade, which is obviously the full model from the beginning, which you have most likely class membership for. And then so the idea is, how quickly can we know who these 46 people are? Well, with kindergarten only, we can identify 28 of them, but 18 of them get into the wrong class here with 1 type of error, and 7 with another type of error. So there are 10 plus 8 plus 7, so 25 that we still have not captured. If you go down to kindergarten with 1 measure in the 1st grade, we aren't really doing much better. We still are only identifying 28 of them and misclassifying the rest. Kindergarten plus 2 measures in grade 1 still isn't really doing that great. And then we look at kindergarten plus 3. Well, we're doing a little bit better. We at least have 37 up here, but we still have some misclassification. Kindergarten plus 4, so this is the end of 1st grade. We have 45 that we're capturing with 1 being misclassified, but we're getting 11 extra kids over here that really aren't having problem behaviors. But when we go to kindergarten plus 1, the first measure in 2nd grade, it appears that we're only missing 1, and we're getting only 3 extras that wouldn't have been in that class. If we go further, that's just the last we can do slightly better. But basically, we can identify these children with just 1 measure in, so kindergarten plus 4 in 1st grade and 1 in 2nd grade. So the first measure in 2nd grade. So rather than waiting, until the end of 2nd grade or something, if you can use this type of modeling to determine who these children are by the time they hit the first measurement occasion in the 2nd grade. And this type of modeling, kind of I don't know what you would call it, a measurement prediction model or something, can be applied to many other situations where you estimate a model and then you fix all the parameters and then you bring new individuals in and make predictions for them based on the other model. So if you have people who are coming into some sort of a clinic or something like that and you want to use the information from this study to classify them or something. Okay, I think that's about it. Yep.
Wow. That was quite something, wasn't it? I don't think we could have dreamt about doing that only a few years ago. It's pretty amazing. And I thought it would be useful to say one thing here as a caveat. If you look at slide 162, Linda casually threw up this model on the board and said, here we have a latent transition model. So we statistically allow students to get out of the lowest class when they move from kindergarten to first and second grade. And I thought, well, that's pretty amazing, isn't it? You have a latent transition model embedded in a growth model where the indicators of the latent transition categorical latent variables are the growth factors in the sequential random effects growth model. So yes, that's doable, and actually it's not very hard to do technically. Actually, it's not very hard to get it to converge. But you know, the problem with this, when we talk, we try to span a lot of different kinds of models and try to make you excited about the new possibilities. But sometimes I feel we maybe make you too excited. That is, if you're a beginner in this field and you go home and you want to be doing this on your data, there is a tendency of overexcitement in getting into these complex models too quickly. This comes about by carefully doing analysis that deal with parts of the model. A simple linear growth model here, you can spend a lot of days or weeks in trying to get that right. Maybe it's not linear. And growth model for this part in first grade, second grade. And when it comes to the mixture modeling here, it takes a long while to get that right, and then a latent transition model has to be worked on. So you need to know that you should build up your models very carefully, and certainly not when you don't have the full proficiency yet to get into complex modeling too quickly. We just have to put on the brakes a little bit, perhaps. Having said that, let me try to excite you even more. So many researchers have randomized trials in all kinds of fields, psychology or medicine. In pharmaceutical companies, there are a lot of randomized trials going on. Randomized field trials, interventions in real settings, increasingly use randomized trials. And one very important notion is that you can have different treatment effects in different trajectory classes. Very often in these interventions, you find that there is no significant overall effect, but there is an effect in one or more classes. That is, you can answer the question for whom an intervention is effective. And it may not be effective for everyone. That doesn't mean you have to subset your sample into very small parts and check for whom it's effective. But you can do this subsetting within the modeling through mixture modeling. And we wrote, a group of us who are in the so-called prevention methodology group in the US, a blend of statisticians and psychometricians and psychiatrists and psychologists, working with the real randomized field trials, work together on methodology and put that into a biostatistics article that I recommend for you who are interested in trials. And there's a previous version of on the same theme in psychological methods by me and my former postdoc, Pat Curran, which is a special case of that. And the idea is that you go beyond the ANCOVA situation. ANCOVA has a post-test and a treatment variable that influences the post-test, and you want to control for pre-test to get higher power. So you look at the change in the means of Y7 across the treatment control groups for given values of Y1. So you look at the intercept change here. This is an intercept change. We know that very well because it is a dummy variable influencing the dependent variable. Now, a more thoroughgoing investigation when you have longitudinal data would look at not only Y1 before treatment, the baseline value, and say the last time point, but every time point in between. So you have the intervention taking place here, and you center the growth model so that the intercept is defined at the pre-intervention time point, and therefore the treatment influences S and Q, namely the trajectory, the development, the change in development over time as a function of treatment, not the intercept, similar to the NIMH schizophrenia application. But now we are introducing C that changes the intercepts and therefore the means of the growth factors. So there are different kinds of trajectory classes here, and we allow that these treatment effects on S and Q are varying across the C classes. So the treatment effects, the slopes here, are allowed to vary across C. That's what the broken arrows say. The slopes differ across the classes of C, similar to the complier average causal effect estimation of yesterday's morning. So that is what we have tried to explore in this biostatistics article. And we get more and more schematically drawn model diagrams. Here you have a repeated measurement series of Y. In this case, it was aggressive disruptive behavior in these Baltimore public schools. You have the growth factors. We call them eta here. And I use an ellipse to represent I, S, and Q. And here the treatment control variable is called I for intervention. It's a dummy. And C influences the growth factors. And C also lets the intervention have different effects on the growth factors. That is the model I just talked about. And you can expand it to model 2, where you can also bring in a distal outcome. So this could be aggressive disruptive behavior in early grades. And U can be a court record of criminal behavior by age 18. And you can have the intervention influence the growth differently across the classes. And the intervention may also influence the distal outcome, the court record, and the intervention on both growth factors and on the distal may vary across the classes. And those two models are covered in the article on the left there by statistics. The editor didn't have enough pages to give us to deal with a model with changing class membership across time, but I won't take time to talk about that one. I'll show you some plots instead. Here on your right, the left column is for the control group and the right column is for the intervention group. We found some evidence of 4 classes: a high class, medium class, a low starting but increasing class. And then for each class you can then compare, say that you look at the high class here, compare the control group with the intervention group development. And you see that the intervention pulls down the aggressive disruptive behavior. And so there seems to be an effect in the high class and perhaps also an effect in the low starting class pulling down the development. This is a plot that you can get out of Mplus. Here's another plot that you might want to take a look at. Here is the means that you get out of Mplus. The means over time, say for the 4-class model at the bottom, and I'll put it on the right screen as well. We look at the your left screen, I mean. So here are the means across the time points, 1st grade to 7th grade. And we find that we have 4 classes, and you will have 4 pairs of mean trajectories, 1 for each of the 4 classes. And each pair, say the high starting pair, is control and treatment group. They start out at the same value because they are randomly equivalent at the pre-intervention time point, the baseline. But then, thanks to the intervention, the aggressive behavior is pulled down. And you see that there's a bigger intervention effect for the high starters than for any other group. Actually, for the medium and the low, there's almost no intervention effect. It's only a possible intervention effect for the increasing aggressive children. So that's helpful. So in this actually, growth mixture modeling saved the day with this study because, again, there was no overall main effect significant for the intervention, but there was a significant effect for those who started high aggressive in the fall of first grade. Here's another plot which relates to what Linda talked about on slide 175. Linda talked about how one could look, with continuous outcomes, how one could use, one could look at observed minus expected means, variances, and covariances within each class. So at the top here, you have the means for the control group, and the estimated means, say that we look at the high stars, are in the smooth curve here. These are the model estimated means. So that's the same as what we looked at the bottom left. And then the wobbly curve are the counterpart to the observed means. But of course, observed is a truth with modification. That is, it is not totally observed. We don't observe any class-specific means, right? We only observed one mean, and therefore we have to create a quasi-observed mean, which has been suggested in the statistical literature. And that quasi-observed mean is a mean where we start with the raw data and weight the raw data by the posterior probabilities as weights. So if you if you're interested in the quasi-mean for observed mean for class 1, you use the posterior probability for class 1. So that's the closest thing that you can get to the data. It's not totally observed, it's quasi-observed, but it is at least a way to gauge how closely you get. So this looks reasonably well-fitting for the control group and also for the intervention group here. And you can do these plots not only for the means, but you can also do them for the intercepts. Sorry, for the variances and covariances. Here's the input. It's nothing difficult now at all. We have a 3-class model here. And here is the intercept, linear slope, quadratic slope. And we center at time 1 because we want to isolate the intercept as a pre-intervention quantity. And actually, as is often the case, you do not need the variance or the residual variance for the quadratic factor. It's often a fixed effect rather than a random effect, and you just fix the variance of it to 0. And then here are the regression, the treatment effects affecting the linear and the quadratic slope differently in the 3 different classes. You also talk about the means of the growth factors here, but you don't need to do that. That's handled by default. So there's nothing new there, really. And here you have the corresponding readings on growth mixture modeling. It really started with this biometrics article in 1999. From my point of view, that's where I started. Here is the biostatistics article. Here at the bottom of slide 178 is an early overview article in Kaplan's handbook. And 2008 at the top left is the latest in the series. By the way, here is the reference for the reading data that Linda referred to. And there's also a Journal of Educational Psychology article by Kim Bosgarden on that topic as well, writing from her dissertation. And now, folks, you're thoroughly exhausted and very much primed for some heavy technical stuff, aren't you? No, maybe not. Maybe we should save this for another day, but particularly since we only have about 5 minutes. But let me just say a few things. We have alluded to numerical integration several times, and it is there's an interesting connection between numerical integration, between 3 things. interesting connection between numerical integration, mixture modeling, and non-parametric representation of a latent variable distribution. We talked about the last one yesterday at the end, that sometimes you do not want to assume that the latent variable is normal, but you want to estimate its shape. Maybe it's very non-normal, and we said that we could do that approximated by a histogram. So let me give you at least those connections, even if we don't get into all of the technical details of numerical integration. So numerical integration is a way to express a density. This is a density for a y variable. Density in human terms means a distribution. You want to estimate or approximate a distribution that is, say, normal. You can do that numerically by replacing this integration by a summation over certain number of points here. The more points, the better the approximation. So that you get weights, the heights of these histogram bars, times the evaluated at certain f values here. And the more points, the more histogram points you have, the better the approximation. You can see that yourself. Integrals, you know, we dealt with them in high school math, and they were so nice and explicit, but in reality, they're seldom explicit. And in reality, in computers, you always approximate them by numerical integration. Numerical analysis is an interesting topic. And it boils down to a simple sum. And you sum over, say, 15 points, k equals 15, you get a pretty good approximation to a continuous distribution. Numerical integration uses fixed weights and fixed points. So there are actually books that you can buy and read at night about, you know, the quadrature points and quadrature weights. You can figure them out when you have 15 points or 20 points or 40 points. It's great reading. Puts you to sleep right away. But that's implemented in computer programs. They can actually now compute them. Not only is that interesting for approximating distributions, but you can also think that here you take a non-parametric approach for, say, capturing this non-normal distribution. This looks like a chi-square distribution, and it can be approximated by, say, 1, 2, 3, 4, 5 points, and their corresponding weights. And here, then, we can think of this in the mixture setting, where the weights corresponds to class probabilities. So we have 5 classes, and these are the class probabilities diminishing, and these are the means, the factor means for the different classes. So you actually estimate the weights and the points, the class probability and the class means. So that's a connection between numerical integration and random effects, non-normal random effects distributions. Now here's a lot of text that you can study. And essentially, there are some models, particularly models with continuous latent variables and categorical outcomes, where with maximum likelihood you need to do this numerical integration. That's what that page says. And on slide 184, it says that numerical integration is computationally heavy and time-consuming because the integration must be done at each iteration. Computational burden increases as a function of the number of integration points, increases as a function of number of observations, and as a function of number of dimensions. That is the number of latent variables for which numerical integration is needed. So the worst case is if you have a lot of factors and a large sample, then it is quite slow. So we try to give some general recommendations here. First of all, we note that with only 1, 2, and I would say 1, 2, and 3 latent variables, the computational burden is pretty light. But when you get to 4 and 5 and more, it gets to be quite heavy. We have different kinds of numerical integration options. Adaptive quadrature, as it says at the top left, is a way to make the computations more effective, not choose the same quadrature points at all iterations, but modify them to capture the distribution better. One way of dealing with many dimensions is to do so-called Monte Carlo integration. I will give you references for your self-study at the end here. But suggestion for numerical integration, and this will be very important next week too when we talk about multi-level modeling, is to start with a model with a small number of random effects and add more one at a time. Very often, effects are not random, but fixed. And I alluded to that when I talked about the quadratic growth model. Very often, the intercept has a lot of variation, and the linear slope has variation, but the quadratic doesn't have much variation, perhaps not significant variation, and you can let that be fixed, fixing its variance to 0, and then you would cut out one random effect and have one less dimension of integration. So all of these suggestions are good. You should read them here. It says with more than 3 dimensions, you could reduce the number of integration points to 5 or 10, or use Monte Carlo integration. Sometimes if you reduce the number of integration points too much, you will get optimization problems, which are shown in the technical output number 8, where you get negative improvements in the likelihood instead of improving the likelihood continuously. Well, here's for those of you who like statistics. It's a beautiful page, but I will not talk about it now. And instead, point you to numerical integration. For those of you who are techies, and there are a couple of technical people here, I know. Bach and Aiken apply that kind of numerical integration in item response theory. This is the theory that underlies the so-called bilog program in item response theory. They use the same procedures we do. Let's see, Schilling and Bach here at the bottom is a recent one talking about high-dimensional maximum marginal likelihood item factor analysis by adaptive quadrature. And there's also a very good it's a good overview in Vermont, and I should say, I guess I don't have it here. Let me see, I think I have another reference at the very end here. That's a good overview of this. Here it is. This book is recommended. Here's Anders Grondal that I referred to earlier. They have a good latent variable modeling book by Chapman and Hall. And somewhere in this book, it deals with structural equation modeling, longitudinal multi-level modeling. And somewhere in this, they deal with numerical integration very more seriously for those of you who are technically inclined. So that's a feature of maximum likelihood estimation. And we are inclined to use maximum likelihood estimation, particularly for mixtures. On Monday and Tuesday, we will see other estimators that avoid numerical integration. And you probably will hear more about that topic when version 6 comes out sometime in the future. So with that, folks, I think we have come to the end of the day, and we hope that we'll see many of you on Monday. And we'll have a cozy little gathering on Monday with only about 190 participants. For some reasons, the multi-level topic seems to be the most popular right now. So
we should have questions.
Let's see if anybody has energy at this time of the day to answer or to ask some questions.
Oh, here we have.
Yes, I seem to wake up that late in the day. I have a question concerning the exciting model you presented, Linda, on slide 162.
162? Okay.
Slide 162.
And it is actually a question about the strategy you described on the following pages. You said first you estimate the most likely class membership
you
with
mean-
the full model.
Okay, so you're talking about how we create the table.
Yes,
Right.
But I think it's it's the easiest to understand with this picture. And then
Okay.
you started with a kindergarten growth model as a first step.
Right, so first you estimate the full model.
Exactly,
And you get most
yeah.
likely class membership. Then you estimate only this part of the model.
Yes,
Whoops,
And-
this part of the model.
exactly. And that part I understand. With the next step, I have a problem because the grade 1 growth model is pretty poor if you use just the first measurement point. It's
Right, if you use the first measurement point, then which parameters, would be involved? Well, that first measurement point points to I1 and I2. So you would have to have, I1 would be fixed at 1 and I2 would be,
I2 and S2.
no, I'm sorry, I2 and S2. I2 would be fixed at 1 and S2 would be, I think it's -7. So that would be fixed at -7. And then you would fix the growth model, anything related to the growth model parameters at what you had from the full model.
So there's no parameters estimated. So you don't have to worry about having too few time points to identify the model because you already have the estimates from the full model.
So everything's fixed. So you use the ampersand or whatever you call it, something, every single parameter is fixed. So when you run it, nothing is estimated, you just get most likely class membership.
And an additional question to this analysis, did you test if you need the kindergarten measurements at all to determine the class membership? Because it seemed like you get a good classification when you include, up to 0.5 in school. Do you need kindergarten?
You wouldn't be able to see the trajectory that people are in, I don't think, if you just started measuring them in first grade. I mean, they would still be low, but I think you would get a better picture if you have the kids starting in kindergarten through second grade and you have the opportunity to measure them, then I would think that you would get more information from that than just starting in first grade.
But it could be a design issue where you could ask, is it worth the investment in measuring
Right.
early? Once you have these data, you could throw out kindergarten and
then-
try only the first WR1 through 4, start there and see if that's sufficient.
And that's like what I was saying, is that you can get a prediction model, and as long as the people that you're using, that you're predicting for, that weren't involved in the original ones are from the same population, then this model could be used as a prediction model for people from that population.
So it's an interesting idea that Linda presented here, that you have, you're using the model as a measurement instrument. You have all of the parameter estimates, and all you need is one, you can do the analysis with one person, because you fix all of the parameters, you estimate no parameters, you just stick in the data for one person, and Mplus spits out the posterior probabilities for that person to be classified. It's an interesting, we do all this estimation, but we seldom talk about, well, once we have the estimated model, how do we use it? And you use it as a measurement instrument, for anybody who can be thought of as sampled from that same population. So
I've seen this being done with logistic regression models. You test, once you've got the parameters, you test the model, see how many cases you misclassify.
Mm-hmm.
It's a standard way of testing how good the model is at
yeah,
fitting
that's along
data.
the same lines, yeah. But I haven't seen it done for growth models, and certainly not for growth mixture models where you want to predict membership early on, for instance, in the prostate cancer situation. So we mix prostate cancer and child development here freely, just to fit your particular application area. Actually, quick survey. How many of you work in the field of psychology? How many of you work in the field of marketing research? And what about psychiatry? And what about in education? And what about medicine? What else is there? Oh, sorry,
I was just going to
statistics,
say
I forgot.
criminology.
I denied my own field. Okay.
I always wished I had studied criminology. Oh.
Yeah, Linda wants to solve crimes.
I do. I want to be a detective.
Okay, more questions.
I have a question on page 153.
123?
153?
Yeah.
153?
Could you please explain again why it is not necessary to include the regression statement of the distal outcome in the structural model part?
I don't get.
Yeah, so the question is why don't we have to include the regression of the distal outcome on C, on the latent class variable? Mplus could be trained to accept saying distal, say D on C, and in the future we might do that. But that is exactly identical to, if you have D on C, it is like dummy variable regression. C is a dummy variable, say if you have two categories. So it changes the means or the intercepts or the thresholds of the D variable. And that's exactly what we have here on the right screen. We have the thresholds do vary across the classes. Actually, by default, they vary across the classes, so it's not needed. So by default, it's already included in the model, this relationship between D and C.
So there is a standard assumption or default assumption that the covariate which is included in the use variables and is not used in the structural part, that would be the distal outcome.
Exactly. So if the variable is on the use variable list, well, we don't have a use variable list there on the left, but it's not mentioned in the model, it will be treated that way, yeah.
Okay, can I also use several distal outcomes in
Yes.
one model?
Yes.
Yes.
Okay.
With
Would
one caveat, you have to be, with several distal outcomes, you have to be careful because by default it says that you have conditional independence between those several distal outcomes given the latent class variable, and you may, which is a latent class analysis type of model for the distals, and that you may or may not want to have that. So that's just something to think about, and you can probably modify it in some way.
Add with statements?
Yeah, in some settings
Right.
you can.
Okay.
Yeah. All right. More questions? There are 2 minutes left.
General question relating to latent class analysis of different types, like also latent transition analysis. So when you include covariates, this might change the classification or class memberships. So is this a frequently occurring problem, and how would you handle that, and what is the sort of the criteria for this? What is too much of a difference when you add covariates and the solution is changing?
It sounds like a difficult question. Would you like to answer that?
If you could repeat it.
So yeah, so the case of latent class or latent transition analysis, when you have covariates and you do the analysis and decide on a number of classes and you get certain class probabilities without covariates, and then you include the covariates and they change. The class probabilities change, and if you search for the certain number of classes by BIC, that decision may also change when you have the covariates. So what do you do?
Well, that probably means you have direct effects in the model, or that you need to specify direct effects so that you have some type of measurement invariance going on for your outcome variables.
Non-invariance, you mean?
Non-invariance, right, for your outcome variables. So you would want to look at the relationships between the covariates and the outcomes and see if you have significant effects, which would indicate that you have a direct effect.
So again, if the true situation is that the covariates influence C only, and therefore only indirectly influences the outcomes, there should be no statistical difference between the two approaches. So if there is a difference, it's most likely for the reason that Linda mentions. Well, that's a field that several researchers are doing investigations to try to learn how to do that more wisely. Okay, more questions? By the way, how many of you are involved in randomized trials? All right.
Just a few. That's tough.
And anybody here from the pharmaceutical side of things? No, not here.
Okay.
Okay. I'm just asking you instead while you think about your questions.
So-
All right.
so
So,
now-
are you going to work on Mplus then tomorrow, Sunday?
We're going to go sightseeing.
We're doing sightseeing. Well,
right.
folks, thanks, and I hope to see you, many of you, on Monday.
On Monday. Thanks a lot. Bye.